All right, let's resume our discussions on the network flow. Um, Last time we were talking about running a greedy algorithm to solve the problem. Let's briefly recap the problem, the algorithm, and also mention again about the problem we are going to encounter by using this greedy algorithm, and finally we are going to talk about a way to fix the problem. And then after that, we are going to talk about one of the major theorems in this chapter, like the Maxwell mean cut theorem, and that's actually the as I mentioned, that one of the first primordial result. I think like in for most of you, like this is the first time you see this kind of result. Um, this algorithm is actually pretty straightforward. So basically, what we need to do is we start with imagining we have a clean network, and what we are going to do is to gradually push up the flow that's coming from S and arriving to T, right? Every time, what we need to do is really just to find a path that allows us to send more flow along that path and push up the flow, and then we repeat these actions until we cannot do this anymore, and then we will find some sort of local optimal, right? So the first step is pretty straightforward. What we need to do is really just to find a path that's an arbitrary path that's connecting from S to T, and then push up the flows, right? In order to find the path, we can either run BFS or DFS, right? So let's just imagine that when after we run on BFS, we come up with this path, the path that's over here, right? So now, because in the beginning we are not sending any flow at all, so basically the next thing we need to do is really to calculate the amount of flow we can send, additional flow we can send for each of the edge, right? If you look at the first edge, this is the first edge, right? So basically, because as I said that we start with empty flow, whereas the capacity limit here is 10. So that means that we are able to send 10 unit of flow along this path, right? Similarly, if you look at the second pass, right? So in the beginning, the flow we are sending is 0, whereas the capacity limit is 8. So we get an 8 here, and we can repeat the same operation for the third edge, and we can sort of see that we can send a 10 unit of flow for the third edge, right? So now at the end, we sort of want to decide the total amount of flow we are going to send along this path. What we need to do is really just to compute the minimum of all these three numbers, and then we get an 8, right? So this is the minimum of 10, 8, and 10, right? So this is the 8 over here is more or less a bottleneck. And that means that we can really just send the a unit flow, a unit of flow along this path. If we send more, then the second edges do not have enough capacity, and then we are not going to successfully push this flow from S to T, right? So what we need to do next is really just So what we need to do next is really just update this network. Just reflect that we are going to send 8 unit of flows over this path we choose, right? So basically, this goes to the graph that's visualized here, right? So basically, the graph here is saying that okay, we are choosing this path, and the next things we are going to do the update, right? So after we do the update, right, if you just look at the numbers here, right, the first edge moves from 0 to 8. The second edge also moves from 0 to 8. The third edge moves to 0 to 8, right? So this is so you sort of imagine that we sort of start to push 8 unit of flow from S to T. So at this moment, the total amount of flow here is 8. Now, what we need to do next is to repeat the same action, right? And find another flow, another path that's connecting from S to T that allows us to push out more flows, right? So basically, if we look at the second pass basically, so I look at the next slides and sort of see what we need to do, right? So the second pass this slide is choosing is really just to choose another pass that's moving from here just as to the one, and let's also label all these nodes, right? So let's just say that the second pass is moving from S to A to B to D, and D to T, right? So now we sort of also see that the question is what we need to do, like what we need to do in the previous iteration. The next question we want to answer is that how much additional flow we can send, right? Additional flow we can send. Right. In order to answer that, right, so we can really just look at the additional flow each of the edge can send, right? So if you look at the first edge again, right, this is the first edge, right? So it's already using a unit of the out of 10 unit of capacity, right? So the additional flow we can send is 10 minus 8 equal to 2. Right. Similarly, we can do the same operations for the rest of the edges, right? So for the second edge over here, the additional flow we can send is 2 minus 0 equal to 2. And we can keep doing the same operation, and the third one would be 9 minus 0 equal to 9, right? This is the third one. And the fourth one would be the 10 minus 8 equal to 2. Right. So now we get the amount of additional flow we can really send for each of the edge. The next thing we need to do is again to take the minimum of all these numbers, right? So if I look at the minimum, right? So if I also draw that heavier, right? So if I look at the minimum, right? So the minimum of all these numbers, right? So it's 2, 2, 9, 2. If I take the mean, I get the 2 over here, right? So basically, the plan is really to push up 2 more unit of flow, out of this new path, new path we have found, right? So now let's also erase what we have done. We have seen so far. Let's just make the picture a little bit clear, right? But we sort of know the conclusion that we want to push up 2 more unit of flow, right? So basically, what we are going to do is really just to add the 2 unit of flow over here, over the entire path, right? So we are choosing this path, right? So that the bolded one is the first path we chose, right? Just don't get confused, right? So for the second pass, we are going to it's highlighting in red. So we are going to add the 2 unit of flow for every single edge, right? So at the end, so this is going the first edge will have 10 unit of flow. The second edge will also have we have 2 unit of flow, right? So now this becomes 2. The third edge will we also have 2 unit of flow, and the third that's the last edge. This is the last edge. The fourth edge is the last edge. Will now also have 10 unit of flow. Right. So this is basically this the next figure we are seeing here is really just that what we are going to see next, right? So after we do the update, this is the entire network so far, right? So you really can see that after this number get updated, the numbers are as what we have computed just now, right? 10, 2, 2, 10. So now let's just look at the next. Now let's really keep doing the same thing, right? So we sort of need to again, like let's just repeat, right? So one of the central argument is really just that find the next thing is that we really just to repeat this what we have been doing. Really find another path, right? Find another path that allows us to push up more flow over here, right? So sorry for that. More flow here, right? So for the next pass we are going to find, right? So we sort of need to avoid, right? So there's one interesting aspect of this algorithm I just didn't mention just now. We need to avoid the edges that are already saturated. Right. Saturated means that if you look at this edge over here, right, it's 8 out of 8. The edge, right? So I'm talking about the edge, the edge I'm drawing over here. It's 8 out of 8. So for the edge E, right? So we are no longer able to push up more flow, So that's the reasons that we sort of need to avoid this kind of edge E, right? So let's also look into how many edges that are already saturated, right? So the first edge, this edge, the bolded one, right? The E1 is sort of saturated. We need to delete that, right? So and then let's also call this E2. E2 we also need to delete that, right? E3 over here we also need to delete that, right? So and actually the E4 it also needs to be deleted, right? So the reason I said deleted is really just that next time I really need to find another path that's avoid using any of the saturated edge. Otherwise, we cannot use the path to push up more flows, right? So if you just imagine that the green path I'm drawing here, right? So it's a legitimate path, right? But then for the E1, right, because we use the edge that's saturated, basically it's already using 10 out of 10 units, right? So basically that means that we are unable to push up more flows, right? So basically that really also means that even we manage to find a path that's connecting between S and T, we will not be able to update the flow and make it larger, right? So the central problem here is that if we don't delete those saturated edge, then there's a chance we are going to end up with finding the passes like the green one, right? So but after we delete all these edges, right? So let me just write this down, make the whole thing bolder, right? So after, okay, needs to be kept, right? So after we delete all these edges over here, right? So now we can run another BFS, right? And this time, then we can guarantee that whenever we find another new path, we can still be able to increase the network flow we are looking for, right? So the next path we found is over this one, right? So again, let's really just compute the amount of new additional flow we can push along this path, right? So this is this we can push at least a 10 unit of flow for the first edge, and then another 7 unit of flow for the second edge, right? The 7 comes from 9 minus 2, right? The 9 over here, 2 over here, 9 minus 2, right? We repeat the same thing. If I look at the third edge, right, it's also, right, it's 6 minus 0 equal to 6, and this is the 10 minus 0 equal to 10, right? So what I need to do is really, again, to compute the minimum of all these numbers, right? So this is 10, this is 7, this is 6, right? And this is 10, right? So 10 comes here, 6 comes here, right? So if I take the mean of all these numbers, right, again, I get a number of 6, right? That means that I want to be able to push up 6 units of flow along this path, right? And not the entire path, I'm going to push up 6 units of flows, right? This is exactly what the slide's going to do, right? So if the slides found exactly the same path as we found, right? So it's not that this is the unique path in most of the cases. It's really just that I read through the lecture and then I sort of know that what path it's going to choose, right? It's, if there could exist multiple paths, basically whatever path you found, that would be a legitimate path, right? So there's no deterministic order of the updating rule. Right, so for the one we are updating here, right, so basically we add 6 units of flow, basically all the numbers along this path is incremented by 6, as you can see, right? So 0 incremented by 6, like for instance, if you look at the fourth edge, right? So now we can sort of, we already see, now after we update everything, right, so this is the entire network we are going to see, right, after we make a number of updates, right? So let's again just delete the saturated edges, right? So if I delete all the saturated edges, and then I will all of a sudden realize that if I look at all the remaining edges, those are highlighted by the green, right? So actually it's impossible, right? Impossible to find new passes, right? And then now eventually we get the network flow of 16, right? So if you look at all the numbers, when you sum up all of them, it's a network flow of 16, right? So last time we were sort of mentioning that this kind of algorithm actually doesn't give you an optimum solution for this particular network. It turns out that the optimum solution is 19, right? So this is the optimum solution given here, right? So it's a bit buggy, right? So in the sense that this algorithm is sort of at least it doesn't always work. But then, as you will see, that we just need a minor but important tweak in order to make this algorithm work, right? So in order to make this algorithm work, one thing we need to look into is that well, at least that it was incorrect for a fairly complex network. As a general principle, when you want to fix the bug of a program, basically you want to sort of find some sort of very easy test cases that can crash the algorithm that's in your mind. And this is actually what the slides is going to talk about, right? So we're going to find a very simple network, right? So the purpose here is that we find a simple network, right? Simple network that can sort of crashes the algorithm. Why does the algorithm can crash, right? So let's really just run our greedy algorithm, right? So just look at here, like the S and T's are the two nodes that are along the diagonals, right? So let's imagine that we sort of again execute our greedy algorithm as outlined before, right? Well, even before we execute our algorithm, we sort of can see that by eyeball inspection, like what's the optimal solution? The optimal solution is really just that I push I push the flows along two passes. The first pass uses the edges that's connecting from S to V, from V to T, right? So the first pass pushes the 2 unit of flow, right? So similarly, you can use another pass that's moving from S to W, from W to T, right? This is also 2 unit flow, right? When you add this up, right, the optimal solution is obviously 4, right? So it's really just that the network is too simple, right? By eyeball inspection, you are already able to find the optimal solution. But now let's also try to execute our greedy algorithm, right, and see potentially what sort of problems are we facing, right? So when we run our greedy algorithm, there's no guarantee where we always find the path find out that there's no guarantee on the order or the passes we're going to find, right? So for instance, if somehow we decide to run a search algorithm, the search algorithm sort of identify this path, right? So this path is actually not, it's not going to be returned by a standard BFS algorithm, but actually as our algorithm, in the description of our algorithm, we were actually not specific about any of the search algorithm we are going to use, right? So there's a chance that we are going to search, the search algorithm is going to return the first pass that's moving from S to V, from V to W, from W to T, right? So when you find this pass, right, so the next thing we need to do is really just to determine how much amount of flow we can push up, right? Again, we take a minion operators among all the three numbers, right? This is 2, 1, 2, right? So and then compute and then get the 1. 1 is really just that we can push no more than 1 unit of flow up, right? So after we determine the 1 unit of flow out, right, so what we need to do is really just to push 1 unit of flow along the whole path, right? It's over here, over here, over here, right? So after that, right, you sort of see a network that looks like that, right? SMW, and this is 2, this is 0, right? So and V, this is 1 unit of pass, right? So we sort of make a mistake, and then we so this is the mistake we are sort of making, right? So as you can see very soon, like why I call this as a mistake, right? So let me just make all the symbols clear, right? So basically I'm using the same symbol as what we. Sorry, let me make a pause here. I noticed that there are some out of sync issues in some of the video recordings. I have been reviewing our previous recording. It seems that the out of sync issue gets more serious recently. So in case you have some trouble and then this becomes too disturbing to you, maybe you can just point to me which lecture video has this kind of serious problem, and maybe we will find some way to fix that. Right. So let's head back to the problematic instance we were talking about. So the instance basically says that looks like that, right? So excuse me. I have a network that consists of 4 nodes, right? And the capacity looks like that. All the capacities are 2, and except the middle ones, right? Let's also call these 2 nodes A and B. And I want to run our greedy algorithm, right? Imagine that in the first step of our greedy algorithm, pick up this green path, right? 2 to 1, 1 to 2, right? And now we're going to do the update, right? So the bottleneck here is 1, right? So we're going to really just push 1 unit of flow along the entire path. Right? So after that, this is going to be the network we are going to obtain, right? So this is A and this is S, right? So let me just draw everything again. So this is T, right? So now let's just look at the how much remaining capacity we have, right? From S to A, because we already used the 1 unit of flow, right? The remaining capacity one is 1, right? So let me just write this down. This is the remaining capacity. Remaining capacity. Right, so I can also repeat the same thing and then sort of like calculate the remaining capacity for each of the edges, right? Now it looks like that the sort of the entire networks looks like that, right? So basically we can sort of delete the edge in the middle, right? So in the sense that let me just change a different color, right? This can be deleted because the remaining capacity is 0, right? So now on top of this network, if we run the greedy algorithm again, right, what we are going to get is that we are going to push up one additional flow over the path that's from S to B, from B to T, another unit of additional flow from S to A to from A to T, right? So now, basically, at this moment, we are going to have 3 flows, right? The first flow will be S to A to B, B to T, right? So S to A to B, B to T, right? Right. This is the first flow we are going to get, right? The second flow would be S to B, B to T, right? Right. This is another flow, and the third one would be S to A to T, right? So basically this is what we are matching here, right? So we have 3 flow, and then we are really just need to overlay, right? Sort of integrate this 2 flow and come up with a solution. The solution looks like that. The solution looks like S to A is 2 unit, and then A to B is 1 unit, A to T is 1 unit, and B to T is 1 unit, and then S to B is 1 unit, right? So this is 2 units, sorry. So let me just repeat, right? So we sort of had this 2 solutions, 3 flows, right? So these are the 3 passes we managed to find, one green one and the other 2 blue ones, right? One green one and the other blue ones. And if we carefully integrate these 2 solutions, this would be the final solution we come up with, right? So basically we managed to push a total number of 3 units of flows out of this network. Whereas you can see that the optimum one, right? Let's just compare against the optimum one. The optimum one is actually pushing 2 units of flow along S to A to T. Another 2 units of flow from S to B, and B to T, right? So these are the optimal one, right? So let's really just compare, like what's the difference. The key difference here is really just that we sort of utilized the edge that's moving from A to B at the very beginning, right? So this is sort of a very early mistake we make, right? And after we make this mistake, then basically it becomes hopeless to come up with the optimum solution, because so long as we decide to use the edge that's moving from from A to B, then there's no chance for us to come up with a optimum solution. Right. So also just remember that, like, after we let's really just review like what really went wrong here. Now there are some subtle details going on, right? So these are the flow network, right? So let's also compare with the capacity network, right? Flow is really what we have done, and capacity is really just the limit, the fundamental limit of this network. S to A, S to B, and then A to T, right? So this the flow network looks like that. This 2, 1, 2, 2, 2, right? So these are the capacity network. This is the part of the input of the graph, right? So if we look at this 2, right? So we compare against this 2, right? We sort of have some sort of what do we mean by residual? Right, residual network is really just that what are the additional number of additional amount of flow we can push, like sort of along this network after we sort of utilize this part of the capacity to entertain the flow, right? So the residual we compute is probably looks like that, right? So 2 minus 2, right? So 2 minus 2 is 0 here, right? So it's also 0 here. This is 1 minus 1, and 2 minus 1 is 1 here, right? And then 2 minus 2 is 0, and this is 1, right? So this is the residual network we thought we were able to compute, right? So all these 3 edges are deleted, and the only remaining edge would be A to T and S to B. Right, so that's the reason we sort of came to the conclusion that we can no longer improve the performance of this flow.